When you double click an app, what do you think? What actually happens behind the scene? Your app doesn't magically opens out of the blue. It travels through storage, memory, and the CPU, step by step. Today we'll follow that journey. Before you run any program, it lives in storage, like SSD. And at this stage, it's just a file, a collection of bytes. Just like we have discussed in the last video where we were discussing about storage and file and how in the SSD it's just collection of bytes. And it's not running yet. It's just a data. And when you click the program, the system loads that into the RAM. Why? Because CPU cannot execute directly from the storage efficiently. And RAM is the working area. So for example, this is a short example. Whenever you are eating, so your dining table act as an SSD. Your dining table is like SSD. Your data is present there, right? Your data is present there. Now, you don't eat from this dining table, right? You eat in a plate. So you can consider this plate as RAM. And your mouth will be like your CPU, where you will process the food, just like we process the program. So, and in this plate also, it will not go automatically to your mouth. You will use your hands, like hands. So these are like registers. These are more closer to the CPU than RAM. So the flow is like whenever you are running any program from SSD, it will get to the plate. That is RAM. Just like the food. And to eat that food, you have to get that food into your hands. Just like registers. And then you can eat that. Just like you can process the program in the CPU. So this is the flow. Now CPU enters in the picture after this SSD thing and RAM. The program counter points to the first instruction. Let me remove this. The instruction cycle also we have watched in the previous videos. So the program counter points to the first instruction. CPU begins the instruction cycle that we have learned: fetch, decode, and execute. Now inside them, execution is totally organized. Two important areas are there. First one is stack for function call, and second one is heap for dynamic memory. Whenever you any function runs, it uses the stack. So you call so stack is like it follows last in first out. We'll see it in details in the next video, but for now you can just see it's like a storage kind of thing where the element you put first will leave last, like this. And then there is a heap. It's just used for the dynamic memory. Whenever program asks for a memory at runtime, it uses heap. And any function call, it uses stack. For every function call, it will stack another call here. During execution, what we saw as a flow from storage, our program or file or data goes into RAM, right? And from RAM, it goes to registers. And CPU loads data from RAM to registers. Registers are where the real computations happen. Let's say you click login button. That triggers new instruction. New data enters the RAM. Now CPU is going to process it. Maybe it can be anything, like comparing your password has. So like this. Instructions by instruction. Every instruction got loaded into RAM and then CPU process it. Now, here's where things get interesting. If input is not handled properly, it may override the memory also. So this is what attackers exploit in real case scenario. If execution flow changes, CPU may run unintended instruction. And that's what attackers misuse. They can put their instructions in between and they can change the flow to follow their instruction and execute their program, which can harm our system. Software doesn't break randomly, it breaks in this flow only. So, the journey we have discussed is simple. Programs stored as bytes, loaded into RAM, CPU executes the instructions, and now data moves between stack, heap, and registers. And after that, output is produced. So every exploit we see, malware and bugs, happen somewhere in this journey only. If you understand the flow, you understand where control can be taken. There are many places we saw. Next, we'll go deeper into stack versus heap and why memory layout matters in the security. And remember, we'll keep it simple.